In this video, we're going to discuss another surface called a paraboloid, and we'll focus on elliptic paraboloids first. And then in the next video, we're going to talk about hyperbolic paraboloids. So the general equation of an elliptic paraboloid is x squared over a squared plus y squared over b squared equals z. Now, this could be in a different form. It could be that this is z squared and this is y squared and that's x, or z squared, x squared, z squared, and y. But the important thing is that one of the variables is linear, raised to the power of 1. The other two variables are quadratic, and there is a sum between the two squared variables rather than a difference. So what we can think about given this form is that when z takes on different values, this results in traces that are elliptical. Let's note that. So if we consider, for example, z taking on real numbered positive values, so I'll just say real numbers greater than 0. We'll talk about what happens when it is equal to 0. Then the result will be ellipses or circles, right? Circles are special types of ellipses. We're going to take a look at why this happens. So let's start first with what happens when z equals 0 in this kind of equation. When z is 0, we get that x squared over whatever a squared may be, that's just a parameter, some constant, plus y squared over b squared equals 0. And if you notice, on the left side, everything is positive here because we're squaring any terms, including the constants. So for two things to be positive to add up to be equal to 0, that's impossible unless both terms are 0. So the only way that this can occur is when x is 0 and y is 0. And then we also know that z is 0, so this gives us the origin. Just a point, 0, 0, 0. It's worth noting also here that if we would let z be a negative value in the way that this equation is written, this would be impossible because we have positive terms can never add up to a negative number. And that's why I mentioned here that we're dealing with values for z, or for the linear term, that are greater than 0. Again, if they're equal to 0, it's a point, but these values for z cannot be negative because that would not result in anything in the graph. So let's talk about when we let z take on different numbers in this case. And if we do let z take on different values, greater than 0, for example. Oh, I didn't want to use green there. So let's say that, let's go back to our blue. So if z is greater than 0, then we are looking at traces of our surface on planes parallel to the xy plane. Because z equal to a constant is just a plane parallel to the xy plane. And to explore what this results in, we're going to look at a specific example. But I do want to say that for elliptic paraboloids, when z takes on different values, or the linear term takes on different values, our traces result in ellipses. When the terms that are squared take on different values, so for example, if I look at the xz trace here, and that's when y is 0, the result, something like this, is a parabola. And this is consistent with our quadric surfaces having traces that are conic sections. If we look at the yz trace here, and that's when x equals 0, we get the equation y squared over b squared equals z, which is also parabolic, or a parabola. So elliptic paraboloids have two traces that are parabolas, and then one trace which runs along the axis of the linear variable is elliptical, which is why these are called elliptic paraboloids. So let's take a look at a specific example. We'll also graph it to just make sense of these ideas that we just discussed. And I'm going to move the CalPlot 3D visual a little bit lower so we can work algebraically first on our surface. All right, so let's suppose that the example we're going to look at is as follows. We'll look at x squared over 9 plus y squared over 4 equals z. So here again, this is another example where the linear term is z, which means that this paraboloid will run along the z-axis. It will be symmetrical along the z-axis. When z is 0, we can see again that this will only result in the origin, right? Because the only way that x squared over 9 plus y squared over 4 can equal 0 is if both x and y are 0, so we get the origin. Now, what I'm going to do to make sense of this graph is we're going to input different values of z, which means we're looking at traces on planes parallel to the xy plane at different altitudes at different values of z. So when z is 1, we have that x squared over 9 plus y squared over 4 equals 1. This is an ellipse in standard form. So if we just take a quick graph of this ellipse, look at a quick graph of this ellipse, on the xy plane, on a plane parallel to the xy plane at the altitude of 1, we have that the half of the major axis of this ellipse, which we can get from the denominator of the x squared term, is 3. So we go 3 to the right, 3 to the left along the x-axis, but again, we're at an altitude of z equal to 1, and then half of the minor axis would be the square root of 4, which is 2. So this is the ellipse that we have at an altitude of z equal to 1. Okay, let's take a look at what happens if we increase z a little bit and maybe give it an altitude of 2. See what happens again on a plane parallel to the xy plane, but when z is equal to 2. So when z equals 2, we're going to have x squared over 9 plus y squared over 4 equals 2. I'm going to divide this equation, both sides of the equation, by 2 so that we have an ellipse in standard form. And we get x squared over 18 plus y squared over 8 is equal to 1. So half the length of the major axis is going to be the square root of 18, which is approximately 4.24, let's say. And half the length of the minor axis will be the square root of 8, or 2 root 2, exactly, but approximately that's about 2.83. So we have an ellipse that's slightly larger than the one at the altitude of z equals 1. So at the altitude of z equals 2, our ellipse is a little bit bigger. Half of the length of the major axis, so along x, we're going to go 4.24. So somewhere over here. Somewhere over here. And then along the y-axis, close to 3, and below close to -3. So our ellipse is a little bit larger. So we can see that as we change the altitude of z, we're getting ellipses that are slightly larger in size. And so that results in the graph that we have below. So I already graphed this one. And it's the same exact ellipse that we have. Elliptic paraboloid. You can see that this travels along the z-axis. And as z gets larger, let me shift this a little bit. As z increases in size, is not so easy. You can try it yourselves, but not so easy to move this. Okay, there we go. As z increases in size, we're moving up along the z-axis. We're getting ellipses that are larger and larger in size themselves. Okay. Also, we should note what happens, we talked earlier about the xz trace and the yz trace being parabolas. So let's look at what we get in this particular example. So our equation was x squared over 9 plus y squared over 4 equals z. If we look, for example, rather than focusing on changing the values of z, we consider the trace on the xz plane. If we look at that trace, that will be when y is 0. And we're going to get a parabola, z equals x squared over 9. That's a parabola. And so if you look at our graph above, it's a little bit hard to see. I'm going to have to move it so that we're looking directly at the xz plane. And I don't know if I can do that. Actually, there we go. There's the xz plane. You can see here a parabola. That's the trace that lies on the xz plane when y is 0. And so if we go back below, if we look at the trace on the yz plane, we can obtain that by setting x equal to 0. And when we do that, that's going to give us y squared over 4 equals z, which is another parabola. So if we try again and shift down our visual, I'm going to try, no guarantees here, but what I would do here is try to rotate this so we can look directly at the yz plane, something like that. And so you can see another parabola here. Okay, so there are our elliptic paraboloids. I just want to mention one more time that the example that we looked at was a very specific example, and also the form that we looked at is a specific form. But the important thing is that there's one linear term, two quadratic terms, and if you move everything to one side of the equation, you'll have f of x, y, z equals 0, and the term that's linear will be negative on one side of the equation. So when you solve for the linear term, whether x is x, y, or z, and you have a sum between the quadratic terms, you will obtain an elliptic paraboloid.